My name is Gwen Flowers and I'm a professor of earth sciences at SFU. I'm a glaciologist, and along with my research group, we study what we call the terrestrial cryosphere, or land-based ice on Earth. More than 2/3 of Earth's fresh water is stored in the frozen reservoir of the world's glaciers and ice sheets. These huge masses of ice are formed from the accumulation and compression of snow over time. On a clear day, you can see glaciers from the bus loop at SFU. These water towers represent a valuable resource for the 1.5 billion people who depend on glacier-fed rivers around the world. But they also pose a threat to the millions of people living in low-lying coastal areas because glaciers and ice sheets store about 65 meters of potential sea level rise. Glaciers can also contribute to natural hazards where they cover volcanoes or create unstable ice-dammed lakes. Canada is home to over 1/3 of the world's glaciers outside of Greenland and Antarctica. Here in British Columbia, we have about 15,000 individual glaciers, covering collectively about 25,000 square kilometers. These glaciers supply cold, fresh water to salmon-bearing streams at the hottest and driest times of year. Glacier runoff also contributes to hydropower production, irrigation of farmland, and delivery of nutrients to coastal marine ecosystems. Glaciers and the landscapes they create attract tourism and recreation, and hold cultural and spiritual significance for some Indigenous communities. Understanding how glaciers and ice sheets respond to climate is important for anticipating the downstream impacts of glacier change. Today we'll be looking at a piece of geophysical field equipment that we use to measure glacier thickness and image the ice interior. Ice-penetrating radar uses radio waves to measure the depth and properties of glaciers. The origins of this measurement technique date back to the 1950s, when aircraft radar altimeters intended to measure the height of the aircraft over the land surface appeared to malfunction over ice in the polar regions. The altimeters were actually reporting the distance between the aircraft and the bedrock rather than the distance between the aircraft and the ice surface, because ice is nearly transparent to radio waves. This was terrible for navigation, but ultimately led to the development of a powerful tool for scientific imaging of glaciers and ice sheets. This instrument is comprised of a transmitter, which sends out radio pulses, a receiver, which detects and records radio pulses, and very long antennas connected to the transmitter and receiver. The transmitter is a small piece of battery-powered electronics that generates a high-voltage impulse, 1100 volts in this case, 512 times a second. The receiver is essentially a digitizer which converts the analog signal from the antennas to a digital signal to be read with a computer, and a computer with purpose-built software that processes and stores the data. The impulse travels through the antennas, which are housed in garden hose for protection and waterproofing. They're just resistively loaded dipoles. That means they're long wires with electrical resistors inserted at specific locations. The longer the antennas, the lower the frequency and longer the wavelength, and the deeper into the ice we're able to see. The antennas transmit and receive electromagnetic energy, which travels through the air at the speed of light and through the ice at a bit more than half the speed of light. The data we collect in an ice-penetrating radar survey are electromagnetic pulses that travel from the transmitter to the receiver. The first pulse we would detect at the receiver would be the one that travels directly through the air at the speed of light. The next prominent pulse we would probably see is the one that goes down through the ice and is reflected off the bedrock interface and travels back up to the receiver. By timing the amount of time it takes for that wave to travel through the ice and back up to the receiver, and knowing how fast it travels, we can then estimate the depth of the glacier. When we put enough of these profiles together, we can make a three-dimensional model of a glacier. In this case, one that also shows where the ice is warmest. These measurements allow us to assess the health of these icy reservoirs and provide other information we need for the computer models used to make predictions of glacier change. Direct measurements of glacier thickness and properties such as temperature are critical for estimating potential sea level rise due to melting ice and for evaluating freshwater resources in a changing climate.